Hi, I'm Barbara Andrews, and in this session, we're training a model, which is powerful. But the real value shows up when the model starts doing work on real data at scale. In this section, you'll learn how to deploy a model to an Azure Machine Learning batch endpoint, turning a trained model into a service that can process large volumes of data in scheduled or on-demand batch jobs. Think of scenarios like scoring thousands of loan applications overnight or generating churn predictions for every customer each week. With batch endpoints, you can run model inference reliably, efficiently, and on an entire data set. The result is a production-ready scoring workflow that integrates seamlessly with pipelines and automation in Azure Machine Learning. A batch endpoint turns a trained model into a scalable batch scoring service. Instead of predicting one record at a time, you deploy the model to an HTTPS endpoint that triggers a batch job, typically running on an Azure ML compute cluster, to process many inputs at once. The results can be written back to the data store connected to the workspace, making batch endpoints ideal for integrating with broader data pipelines. For example, a retailer may run a nightly job that scores millions of customer records for churn risk. A data pipeline, for example, from Azure Synapse or Databricks, calls the batch endpoint, which launches the scoring job and stores predictions for downstream analytics. Best practice is to use a batch endpoint for large asynchronous workloads and connect them to your ingestion pipelines so predictions run automatically whenever new data lands. Before a model can generate batch predictions at scale, you first create a batch endpoint, an HTTPS entry point that Azure Machine Learning can trigger for large batch scoring jobs. Using the batch endpoint class in the Python Software Development Kit version 2, you define key properties such as endpoint name, which must be unique within your Azure region, and a description. Then submit it with the ML client batch endpoint begin, create, or update function. Once created, the endpoint becomes the gateway for launching batch inference workloads in the workspace. Imagine a retail team that needs to run an overnight job to score thousands of transactions for fraud or churn risk. Their data pipeline calls a batch endpoint, which scales Azure ML compute to process the entire data set and save predictions to the data store. They benefit with fast, cost-efficient, large-scale scoring without impacting live apps. Consider using batch endpoints for high-volume, scheduled inference tied directly to your data pipelines. A batch endpoint can host multiple model deployments, giving you the flexibility to manage different versions of a model in one place. When you call the endpoint to run batch scoring, Azure Machine Learning automatically executes the default deployment, unless you explicitly specify another deployment in the request. This design lets teams safely manage and update models while keeping integrations stable. Consider a scenario with a fraud detection workflow that scores thousands of transactions nightly. The pipeline calls the batch endpoint, which launches a batch scoring job using the default production model, delivering large-scale predictions reliably and automatically. When running batch endpoints, Azure Machine Learning typically relies on compute clusters to process large data sets in parallel. You define a cluster with the AML compute class, specifying details like the VM size, minimum and maximum nodes, and the auto-scale behavior. In the example, the cluster can scale from 0 to 4 nodes, automatically spinning up compute when a batch job runs and scaling down after 120 seconds of idle time to save cost. The code imports AML compute from Azure AI/ML entities, and it defines a compute cluster and ends with submitting the configuration to create or update the cluster in the Azure Machine Learning workspace. For example, a real analytics pipeline scoring thousands of transactions for fraud or churn, when the batch endpoint runs, the compute cluster scales out to process requests in parallel, finishing faster and handling high-volume workloads efficiently. Here's a pro tip. Configure clusters with the minimum instance equals 0 and an appropriate maximum instances to balance speed and cost. This lets Azure ML automatically add compute for heavy batch scoring and scale back down when work is done. Imagine you've trained a diabetes risk model with MLflow and now need to score thousands of new patient records overnight. To do this, you deploy the model to an Azure Machine Learning batch endpoint using a batch deployment, which defines how the batch scoring job runs and where results are written. Azure ML then runs the automatically generated scoring script across multiple compute instances in parallel, enabling large-scale predictions far faster than processing records sequentially. The benefit here is that batch endpoints turn score a mountain of data into a fast, scalable, automated job that writes predictions where your pipeline can immediately use them. The deployment settings control how batch scoring runs and how predictions are written. Instance count sets the number of compute nodes. Maximum concurrency per instance controls parallel runs per node, and mini batch size defines how many input files each run processes. Output action decides whether to return a summary or append predictions, and output file name specifies where those results are stored. Here's a pro tip. Turn instance count plus maximum concurrency per instance plus mini batch size together. Start small and then scale up until you hit the best speed-cost balance, and use append row when downstream tools expect a single prediction file. Imagine a logistics team turning daily batch scoring to predict delivery delays across thousands of new shipments. Instead of manually wiring inference each time, they deploy a custom non-ML flow model to our Azure Machine Learning batch endpoint, so scoring runs automatically, scales cleanly, and produces consistent outputs for downstream dashboards and alerts. To make that deployment happen, you must already have a batch endpoint, and then you deploy by first creating a scoring script, then an environment, and then the deployment. The scoring script is the runtime contract and must include an init, which runs once to do expensive setup like loading the model, and a run function also, which runs for each mini batch to generate predictions and returns a pandas data frame or a list array. Next, you define an execution environment, either a Docker image with Conda dependencies or a Docker file, and include Azure ML Core, which is required for batch deployments. Finally, you configure and create the deployment with the batch deployment class to bind the model and the scoring script and environment to the endpoint. Remember to keep init focused on one-time loading and make the run function efficient for many batches. Those two choices have the biggest impact on batch throughput and cost. Invoking a batch endpoint kicks off an Azure Machine Learning pipeline job that processes a dataset at scale. You simply pass a data input, often a registered folder or a data store path, to the endpoint using the Python software development kit, and Azure Machine Learning launches a scoring job and writes the predictions to the workspace's default store. The Python code here demonstrates how to trigger a batch scoring job end to end. It imports input from the asset types. It defines data input pointing to a registered folder, and then invokes the batch endpoint with the ML client batch endpoints invoke. Directly beneath the Azure Machine Learning Studio's Jobs tab, you can see the resulting pipeline jobs and their statuses, highlighting exactly where you can monitor each batch run and track its progress. Using a data pipeline, you can register a folder of new daily customer records, invoke the batch endpoint, and Azure ML launches a pipeline job that scores the entire data set in one run, delivering fresh predictions for analysts and downstream workflows. When you invoke a batch endpoint, Azure Machine Learning actually runs a pipeline job behind the scenes. In Azure Machine Learning Studio, you can open the Batch Endpoints Job tab to see each run and its status. If a job fails or behaves unexpectedly, you can drill down into the child job, which represents the batch scoring step, and inspect its output plus logs to diagnose the problem. Inside the log user folder, you'll find three key troubleshooting files: the job error text file, which is a summary of errors produced by the scoring script; the job progress overview text file, which shows progress details, including how many mini batches have been processed; and three, the job results text file, which has errors related specifically to the init or run functions. In the scoring script, if you need to use batch job scoring, thousands of customer records for churn, and the job fails, the logs quickly reveal whether the issue was a data processing problem or an error in the scoring code, allowing you to fix it and rerun the job faster. In this demo, we're going to run an Azure Machine Learning job, which is the fundamental unit of execution for everything from training to evaluation in production ML systems. You'll see how a job packages your code, data, environment, and compute into a single traceable run, making experiments repeatable, able to audit, and scalable. This is where notebooks turn into operational workloads and where ML Ops really begins. Understanding how to run and manage AML jobs is core to AI-300 because every pipeline, sweep, deployment, and automation you build is ultimately powered by jobs running reliably behind the scenes. So AutoML is the click and run experience in the Studio UI. However, if you would like to see something similar, but in Python code, consider our ML Flow Tracking Lab at aka.ms/AI300 Track ML Flow. It offers best model selection and a full experiment tracking. In this demo, we're going to start talking about how to work with an Azure Automated ML to train a diabetes prediction model with real data set without using any code. Now, you may have noticed that this is similar to an earlier one that we did with code, and I want to show you a little bit about how you can do this without writing any code. And the goal isn't to build a model here. It's to understand what automated ML produces and why it matters for our ML ops and where it fits into the entire AI lifecycle. So what we're going to do is we're going to start off right here inside of Azure Machine Learning, and we're going to be able to go work over here on the screen, and we're going to go directly into Automated ML right here in our studio. So when we go into this area, what you'll notice is we can click on a new Automated ML job. And as we make this new job, what we'll note is that we have to come in here and we can move through the GUI. So the first thing we want to do is we want to give the job a name, and when we can change it out if we need to. And here I'm going to change it out to something else. I'm going to name it, let's see, I'm going to call it Auto. Let me clean this up here first. I'm going to call it Auto Diabetes Demo. And what we're going to see here too is it comes up with an experiment name. And I'm going to use the same name. And I'm going to change this out to EXP for experiment. Now I could also go in and put a description and add tags and all of that, but I'm not going to do that. And I'm going to go ahead and I'm going to click on next. And when we get to the next area, if it wants to know the type of task that we want to do. Now, given that we're going to be using the diabetes information that we've been using for a lot of our demos here, this is going to lend itself really to classification. However, you notice there are other options that you can choose in here, and you can pick from them from the list. And I'm going to choose classification for this example. And with our diabetes information, I'm simply going to choose that this is our data set next. And so then it's going to get me to where I can go in and I can tell it which target column I'd like to use. So this is a good option now to kind of set the target column, which is the column in our data set that contains the value that we want the model to predict. And what I'd like it to do out in these fields here in our table is we want it to predict diabetic. So given that information, we might want to be able to predict if someone is diabetic or not. So I'm going to choose that option, and then I'm going to scroll down a little bit here, and we're going to see you can do some deep learning in here. Now we're not going to enable that. Find a little bit more information if you want to find out more. And what we want to do is maybe take a look at a few things in this option here for viewing additional configuration settings. And I'm going to click on that. And so you can kind of see a little bit of what's in here. So this is the primary metric, and this right here is really defined by the classification that I chose, the task type. That classification modeling is there also. And then the reason it's available here, it has AUC weighted. And there's one option in there, but this one works actually really well, a really good option for our classification task type that we selected. So that is going to give us the ability to help us make predictions, and it's going to give us some metrics such as the AUC here that's available. So this is going to be very useful. It's commonly used when we want to be able to get a little bit more accuracy, and not just accuracy, a little bit more than accuracy. And then we have other options we could select here, and I'm going to go in and I have a little bit, so some of the models here, if I click on this, I don't want to use. And I'm going to have it explain best model. And again, you can click on some of these and get a little bit more information if you need that. You can also, I'm going to have it go in and show some of the models in a moment. And then you have the positive class label I could put at the bottom here. And I'm just going to save this, and I'm going to look at some of the other options here. And we have the ability to look at our featurization settings. So I'm going to click on that, and this will take a little bit to populate here, but notice it's set to auto. So when we talk about featurization here, this is going to automatically transform our raw data into model-ready features when this is enabled, and it's enabled by default when we use the wizard here for the automated option. And we're working with, and those transformations are consistently applied during both training and the inference, and also for reducing manual preprocessing to prevent training serving drift. And so really, in short, we take raw data, we add the featurization, and it gives us model-ready features. So it's on by default, and it's a good option. to use here, and it should automatically choose the appropriate transformations based on the data types in the fields. And it will also apply our data guardrails, prevent some of the more common issues like missing values and high cardinality. So all of that is here. And again, it's turned on by default. And this is a good one to use when you're using AutoML. And so I'm going to go ahead and I'm going to save this. And then what we'll do here is we have the limits that we can turn on. And so you can see some of the limits we can do here: max trials, max concurrent trials, number of nodes here, maximum threshold here, also metric score, experimentation timeout, iteration timeout. All of this we could do, enable early termination. If we would like to do that, we can turn some of these on. So I can set all these up here, and I'm going to leave it just the way it is right here. Then the validation type here, we can choose this, and we have a lot of options to choose from. And we're going to select automatic. This is actually best when we're kind of unsure and when our data is maybe medium to large. This is usually the fastest and most efficient option, where we just let Azure choose the best method for our data. We could also, of course, go into k-fold cross-validation. This is going to split the data into k-folds and trains k-models for us. And we want to use that when our data is small and when we want maximum reliability. But it will take a little bit longer to do that k-fold cross-validation. And we should also have it do the Monte Carlo cross-validation. This is a random train and test split. And then it's going to go in and do the test repeatedly over many times. And you can use this when you have a very large data set or when you want robust variance estimates, and it's going to help us. You could choose the train split validation. This is a simple split. It's very fast. You can use it when your training is expensive or maybe when you're trying to do some prototyping. And then you'll also have that user validation information. And that option there provides you with a separate validation data set. So when you provide a separate validation data, it helps us. And right now, I'm just going to choose automatic. And then to test the data, we have nothing here. And none is the option here when we're only training a model and maybe not evaluation yet, or maybe the evaluation will be handled someplace else. If you choose the option none, however, you won't get the validation metrics, such as accuracy or AUC, like we're used to seeing. You could also choose the train split, which is the one that we're going to use here. And this will automatically split our data into training data and test data. And it is good when you have maybe a single data set and you want to have a very quick and standard evaluation. It's a good option here for what we're doing, a quick experiment or demo. The other one that we see here, test user data, you want to use this when you have your own separate data sets that you want to test. And you could use it for production grade or regulated ML workflows that you're working in. So I'm going to choose train test here. And then you can see it from the percentage there. I'm going to leave that percentage the way it is. I'm going to click on next. And then really the beauty of the AutoML is that you can accept the defaults. They're already set. You don't have to really make a lot of decisions. Now it's giving us a little warning at the top about our personal information. So that's something we could do a little bit of a deeper dive into. And you'll see that it's going to be using a serverless compute, although there are options there that we can work with and we can choose those. And then we can see our virtual machine type. Again, the GPU might be, of course, if you want the resource to run faster, that could be an option. But I'm going to use the CPU. And at this point, because it's just a quick demo, but you may also want to reconsider this for some of the models through automated ML here. And then you can see there is a virtual machine and it's going to be dedicated. I can even make it low priority. There are some virtual machines that I can choose from right here. Actually, there's quite a lot. And I'm going to go choose the default, but there's a lot of options. Classical training, all virtual machines. There's something for everyone and different price points, as you can see. And I'm going to go and use the default that it came up with. Number of instances is just going to be 1 here. And I'm going to go ahead and submit the training job on this. Now, this is going to take a little bit to run. And as you can well imagine, it will do that. But we need to note here is that Azure is now training more models in parallel, which is why it'll take a little bit. And we will use the automated ML because it's going to run faster and in parallel. And it's going to use a number of models. And notice here, it's telling us that it started, and we'll just let it run for a little bit. I'm going to use the models. It's going to use the logistic regression, random forest. It's going to use gradient boosting and all of this and keeping detailed metrics. And we can go in and look at each one. So it's going to take a little bit as it sets itself up here. And you know, there's really a lot of benefits, as you know, to using automated ML. First off, there's no code. Second, it's very, very fast baseline creation on top of it, and it's built on metrics and even the ability to explain the model. And what we have left to do is just kind of let it run for a moment. It'll give us the best option. And then it also standardizes the experimentation, and it's really ideal for tabular data. So it's really a particular type of data that you might focus on. It's also going to take it a little bit to run, and you can see right now that it's running. And let's see if you have any data guardrails. No, there's not any opened up just yet. Any child jobs? Not yet. We also might want to run for just a little bit. It did take a little bit for the models to appear. And through the magic of our ability to pause and start this, let's begin again here and let you know some of the models that have been created. So we see here, we can see a little bit about the summary. You can see the classification. You can view our configuration settings if we need to see those again. Featurization settings are right there. You can see the primary metric that was used. All of this was configured when it was initially set up in our model here through automated ML. And what you'll see with this too is that we can get back into this here. And if needed, we can see different job options. There's the YAML. You can also see if we can go into our data guardrails and see what it did, see if there's anything there. This was a validation split there that it did, so we can review that. The number of folds there is 3. You could also go a little further down in the data guardrails and see that the other validations that it did, so class balancing detection, it passed the feature values imputation, it passed our high cardinality feature detection, and we can get more information on those if we'd like. What I'm going to do is I'm going to go out to our models and child jobs, and here you can see that it went through a number of models, and you can see some of those models here that it used. And then, as you may remember, the one that is kind of on this leaderboard is the one at the top. It's the model right here. It has 99% accuracy here. So this is the highest rated model, and I can go into it. I can see a little bit more here, get some information about it, the sampling it did. I could also go into metrics and see the metrics on that. It had a very high rating, and this is at the top of our leaderboard here. I can also come in here and I can see some of the child jobs, as we saw earlier. We'll run those, if any, and I think the child jobs just a little bit higher up here, but the metrics can be very powerful. Notice you can explore other areas here, and if you want to see a little bit more visualizations in here, you have a couple of other options you can choose from. And remember, some of the visualizations are already there at the very bottom, and you can take a look, that might be helpful. And what we can do from here is we can go back one layer, and we can see our main job here, and we can see some of our child jobs that have been run from this. So the next thing to do with this would be, of course, to deploy our winning model, the model that gave us the highest accuracy. This is the one, and look for that, as you can see in the next section here in a separate video. And what I'll do is I want to highlight through this as a little bit of a wrap up. So what makes Azure Automated ML so valuable is that it removes so much of the trial and error from the model development, and even better when we can use it, of course, here through an automated wizard rather than writing code. So instead of manually testing these algorithms and pre-processing choices, Azure ML does the heavy lifting for you, running parallel experiments, as we saw, applying built-in featurization. And remember, I kind of just went through the model interface and really picked just the defaults. And then it helps you quickly identify the strongest model. And we have the strongest model on the screen right now for us to use for our diabetes prediction that we're using it here for. So this means faster insights, more consistent experimentation, and hopefully a smoother path for data, from data to development. And this automated ML gives us a lot here that makes it really easy to use. It gives us the best model possible in our case, and very easy way to use it through a wizard. So I hope you enjoyed it and look forward to seeing you in our next video. Thank you for joining. Now it's time for our knowledge check. Question 1. You are creating a batch endpoint that you want to use to predict new values for a large volume of data files. You want the pipeline to run the scoring script on multiple nodes and collate the results. What output action should you choose for the deployment? Answer: append row. Question 2. You have multiple models deployed to a batch endpoint. You invoke the endpoint without indicating which model you want to use. What deployed model will do the actual batch scoring? Answer: the default deployed model. You've now seen how a trained model becomes an operational asset through large-scale batch inference in Azure Machine Learning. By using batch endpoints, scalable compute clusters, and repeatable jobs, teams can score massive data sets reliably, cost-efficiently, and without disrupting live applications. This is where the machine learning starts doing real work, integrating with data pipelines, running on schedules, and producing predictions that drive downstream decisions. With batch scoring in place, you're no longer just building models. You're delivering intelligence at scale, powered by jobs, automation, and ML ops practices that keep inference reproducible, observable, and production ready. Thanks for joining us for this session. To continue your learning, watch other videos in this course or explore more on Microsoft Learn at aka.ms/learn.